Good morning, HOD Professor A.K. Chaturvedi sir, my seminar guide, Dr. S.K. Rathod sir, seminar coordinator D.P. Sharma sir, faculty members, examiners, and my lecturers. I am Vaibhav Singh Shekhawat, pursuing my B.Tech from University Department of Mechanical Engineering, Rajasthan Technical University, Kota. Today, I am pleased to be here in front of you all to deliver the presentation on my seminar topic, Hyperloop Transportation System. So let's start. This is the table of contents which we will cover in this presentation. Next, in the first slide, we will talk about the idea of the newest mode of transportation, that is the Hyperloop transportation. The idea was firstly proposed by Elon Musk in his white paper, Hyperloop Alpha 2013. Hyperloop is the fifth mode of transportation. A high-speed train travels at a high speed in a near vacuum tube. The reduced air resistance allows the capsule inside the tube to reach the speeds of 1000 to 1200 km per hour. Why Hyperloop? That's the first question in our minds. As the world is advancing forward, basic needs of human existence also needs an exponential increase. We will be seeing an 80% increase in the average passenger mile distance. The freight tonnage would also be increased by 88% by 2095. So, what will be the solution? Can we build more airports, rail lines, highways, ports exponentially with the demand? The answer is no. These demands can only be met with the new modes of transportation. Next, how does the Hyperloop work? The basic principle is to reduce the resistances, that is the aerodynamic drag and mechanical friction. With Hyperloop, vehicles called ports accelerate gradually via electric propulsion through a low pressure tube. The pod floats along the track using magnetic levitation and glides at high speeds for long distances due to ultra-low aerodynamic drag. Hyperloop generates lift by motion through a medium at high speed rather than depending on buoyancy or static phenomena. Through its transonic operations, Hyperloop implements an aerodynamic designs with an air-breathing flow path, giving the technology resemblance to airplanes rather than train designs. To reduce the resistance further, the front of the tube is a compressor fan that takes the air and redirects it to the bottom of the capsule, thus providing a cushion to the pod. The tube, which rests above the ground on pillars, is made in section so as to absorb movements due to earthquakes and is fitted with solar panels to generate electricity for itself. Now coming to the components of the Hyperloop transportation system, it has 5 components. That is first, tube system and stations. Second is the passenger carrying capsules. And third is the vacuum pump system, vehicle control system, and the maintenance department. Now we will discuss in brief about the tubes and stations. The tubes will be based on elevated pillars except for tunnel sections, while the solar panels above the tubes will provide the system with energy. The ultra-high vacuum approximately at the level of 10 to 8 torque would be maintained in the tube. Each station of the Hyperloop system is to be generally integrated within the tube. It would consist of 3 modules. The first one is the chamber as a part of vacuum tube handling the arrival Hyperloop vehicles, ultimately arriving at the chamber. After the vehicle enters, de-vacuuming of the chamber is carried out. The vehicle proceeds to the second module with the normal atmospheric pressure where passengers embark and disembark the vehicle. After that, the vehicles pass through the third chamber where at the moment normal atmospheric pressure prevails, ultimately departing chamber. Then it spends time until the chamber is de-vacuumed, leaves it and proceeds along the line too. The vehicle handling process takes place at each station of the line. Chambers are separated by the hermetic doors, enabling establishing and maintaining the required air pressure in the above mentioned order. Next, talking about the capsules will carry the passengers. The capsule would operate in the above mentioned low pressure tubes on a 0.5 to 1.3 mm layer of air featuring the pressurized air and the aerodynamics lift as shown in the figure. Under such conditions, they would be able to reach the maximum speed of 1220 km per hour. The maximum inertial acceleration would be 0.5 g, that is equals to 9.8 meters. The vacuum pumps are installed to initially evacuate and later maintain the required level of vacuum inside the tubes and in the stations first and third chambers. Regarding the characteristic of operations within the tube and the stations, the control of safe and efficient movement of vehicles and maintaining the vacuum inside the tube and at the stations will be provided by the convenient traffic control and management systems. Next, coming to the levitation and propulsion part, the Hyperloop will levitate above the track in order to propel the pod. There has to be an interaction between the pod and the track that results in the forward force. Since there is no contact between the pod and track, the interaction has to happen on a distance. capsule will accelerate gradually via electric propulsion through a low pressure tube float above the track using magnetic levitation, and then glide for a long distance at a speeds more than 1220 km per hour due to ultra low aerodynamic drag. In the next slide, the right side figure in this slide shows the comparison between Hyperloop and other modes of transportation. Presented in alpha paper, the Hyperloop described in the paper reduces the travel time to under 45 minutes between LA and San Francisco. Now you can see the detailed analysis of Hyperloop versus other modes of transportation with the help of illustrated diagram along with the graphs. The graph in this slide shows the energy consumption and travel time comparison between different modes of transportation. The Hyperloop track between New York and Toronto will reduce the travel time to 60 minutes with the least energy consumption. The infrastructural cost per kilometer of Hyperloop is relatively high at present, but the travel cost, including maintenance cost, overpowers the other modes of transportation. Now coming to the advantages of Hyperloop, at 1000 to 1200 km per hour, Hyperloop has unconvinced any other mode of transportation for commercial use. Travel time reduced due to no onboarding, offboarding time, frequent travels would also be more. Due to the low acceleration and deceleration rates, energy efficiency is more. As the journey will be in cubes, bad weather conditions would also have no effect. On the financial performance of the Hyperloop system, they are defined by the revenue, cost, profits as the difference between the former two. Consequently, the zero profitability achieved by the competitive prices given the cost would guarantee the bottom line for a stable economic viability of the Hyperloop system. Infrastructural costs as well as maintenance costs can be seen in the tables above. Now, in the Indian point of view, Avishkar Hyperloop, a team of IIT Madras, covered a case study on Hyperloop possibilities in India. The above table shows the economic feasibility of Hyperloop over the high-speed rail system developed in India through this case study. Virgin Hyperloop with Maharashtra government has been working on the first train between Pune and Mumbai in India, reducing the travel time from 4.5 hours to 25 minutes. Next, coming to the challenges faced by Hyperloop. The challenging technical areas are the tube's depressurization, the capsule's air resistance and choke flows occurring around the capsule. There is also a need for effective levitation and propulsion solutions compatible with the velocities being used. The political compatibility to ensure that Hyperloop can be integrated with current modes of transportation would also be a challenging aspect. Now, for the conclusion part of this PPT, Hyperloop will bring sustainability and faster travel with potential to disrupt competing industries once operational by 2030. For now, the energy consumption of Hyperloop is still unclear because of many interdependencies between the design variable and unknown or assumed parameters used in simulation models. Finally, finding a suitable alignment with extremely wide curves and acquisition of private land for construction of an elevated Hyperloop in denser populated urban areas will still be a big challenge. At the end of this presentation, I would like to answer your questions.
What is the Cantor-Width limit in Hyperloop?
Cantor-Width limit in Hyperloop appears when the air forced to pass through the free space between inner tube walls and capsules reaches a critical speed beyond which flow stalls and the capsule starts behaving like a piston. A drag force originated from the pressure differential in the front of and behind the capsule appears and increases exponentially with advance independently of the initial air pressure, which does not even appear in the limit expression. Thank you very much for your time.